Hey everyone, so today we are talking about rate law, or differential rate law. We'll talk about different types of rate laws like integrated rate law later on, but for today we're focusing on the most common one that we'll see, which is the differential rate law. And what this is that we're going to determine a formula that if we change the concentration of our reactants will give us the time or how quick or how slow our reaction will happen. So our goal today is just to figure out how to write a rate law for a reaction when we're changing concentrations up. And you'll see how we'll do that in a little bit. But first, let's talk about what our rate law will actually look like. So our rate law is going to help us determine rate, and it's going to equal rate law constant K times the concentration of one of our reactants to a certain number, which I'll explain in a bit, times the concentration of whatever other reactant we have times another coefficient. So, at some point today, you're going to be determining this rate law. We're going to be mainly finding these letters N and M. So, rate, again, is just how quick a reaction happens. It's usually in molarities per second. Okay, K is a rate law constant. It is different for every reaction, and it has different units based on every reaction, which we will talk again later. So you'll be figuring that out after we do figure out our differential rate law. Concentration A, right? That's just the concentration of reactant A. These will actually have chemical symbols in them when we deal with an actual reaction. So this is just concentration of reactant A. If I have concentration of B, right, it's just the same thing. It's concentration, but not of reactant A, of reactant B. And then M and N are just small numbers that tell us how much those reactants affect the rate. So M and N are small whole numbers that tell us how much molecules collide. Okay? So again, M and N are just small whole numbers that tell us how much molecules collide. These could be either 0, 1, or 2. Theoretically, they could be 3, but you won't ever see that in real-life reactions. Pretty much if it has a number of 1, okay, that means if I double the concentration of A, the rate is going to double. If I double the concentration of B while this number is 1, the rate is going to double. If N or M is 2, okay, if I double the concentration of reactant A, then the rate is going to quadruple. So that's what those coefficients are going to tell us, and that's what we're going to be figuring out. It's going to be how much increasing these concentrations of our reactants will affect the overall rate. How much does one reactant speed up the process compared to the other? But before we start actually talking about how we're going to solve for N and M, we got to talk about reaction order. Reaction order is just the sum of coefficients M and N. Okay, so we add up all those coefficients, N and M, and then that will tell us the overall order of our reaction. So say we have a rate law that is rate equals K, A to the 1, and B to the second. Our overall reaction order, when we add 1 and 2 up, is 3. So our overall reaction order will be third order. Okay. If this was 1, it'd be second order. If this guy was 0, it'd be first order. If both of these were 0, they would be 0 order, which pretty much just means the concentration of the reactants don't affect the rate at all. It will happen at the same speed no matter what. Okay, so I will be asking you consistently, what is the overall reaction order, which is just when we add these coefficients up. I might also just ask you, what is the reaction order with respect to A, which you would say first order. What's the reaction order with respect to B, second order. What is the reaction order overall, third order. Okay, and just be aware again that M plus N, if they equal 0, it is 0 order. If they end up equaling 1, it is first order, which is also known as unimolecular. It's a unimolecular reaction, which means it's just based off of one molecule's concentration. Okay, and once again, 2 and 3, second order, third order. Okay, but if it's second order, it's called bimolecular. And if it is third order, it is known as termolecular. Okay, on the AP exam, they might throw that lingo at you, and you will know that they're just saying if it's bimolecular, it's second order. If it's unimolecular, it's one or first order, and if it's termolecular, it is third order. So here is our first example. How we figure out this rate law is through experimentation. We put it into a lab and we change concentrations, and that's how we'll figure out the rate law. And how we do that is that we end up keeping one concentration of the reactant the same between two trials, and then we only vary one of the other concentrations. That way we know that it can't possibly be the reactant that we kept the same concentration that's affecting the rate. It's got to be the one that we're changing the concentration of. So this is how this will look when we get our data in a table. So what we are going to do is we're going to find two trials or two experiments where we kept the concentration the same. So if you are looking here in experiment 1 and 2, you will notice that for concentration A, we left the concentration the same for experiment 1 and 2. So that means that this did not affect the rate at all or change the rate at all because they were kept the same the whole time. So what we will do is we will ignore those two concentrations completely and just focus on the rate of change in concentration and the change in the rate for reactant B. So right now we are focusing on reactant B. So when we changed the concentration from experiment 1 to experiment 2, how did we change the concentration? Well, we went from 0.1 to 0.2. So we doubled our concentration of reactant B. So since we doubled it, what I'm going to do is I'm going to put a 2 down here to the exponent n, okay? Because that's what we're trying to figure out. We're trying to figure out those tiny exponent numbers in our rate law. So I'm going to put the n right there and try to solve for that later. Equals to what happened to our rate. Our rate went from 0.04 to 0.08. So if we look at that, that looks like our rate doubled as well. So what I'm going to do is I'm going to go ahead and put a 2 right there. So now all I have to do is solve. I've noticed that it doubled for that concentration and our rate doubled. So that means that with respect to B, it is going to be first order. Our n is going to equal 1. So with respect to concentration, B is first order. If I double the concentration, it'll double the rate. So if I go ahead and I write out my rate law, we'll make AM this time since I solved for B first. You could switch them, you could make them whatever letter you want. Right now we solve for N, which with respect to B was first order. So now let's go ahead and let's solve for A. So what we're going to do is we're going to find two other trials where the concentration was kept the same. For concentration B, in experiment 2 and 3, the concentrations were kept the same at 0.2. So that means that B did not affect the rate in trials 2 and 3. It was only A where the concentration changed, where we affected the rate. Okay, so I will cover up the concentrations in column B, and now I am focused on reactant A. So once again, I'm covering that up and I'm looking at my concentrations. So what it looks like is it looked like that from 0.10 to 0.20, sorry, this should be 3.2. Sorry, that should be 3.2. So it looks like from experiment 2 to experiment 3, my concentration doubled. So I will once again put a 2 right there and my coefficient n. So when I doubled the concentration, what happened to the rate? Well, when I doubled the concentration on reactant A, it looks like my rate quadrupled. Okay, it went from 0.08 to 0.32. So I am going to put a 4 right down there. So now, when I put a 4 down there and I go to solve for m, my m is going to equal 2. So with respect to reactant A, it is second order. If I double the concentration of reactant A, that should quadruple my rate. Alright, so that is our rate law. What is the order of this reaction overall? Well, all we do is we add up our coefficients, 2 and 1, which is 3. So our reaction is third order overall. It's second order with respect to reactant A, it's first order with respect to reactant B, but overall this reaction is third order. Next thing I'm going to do is I'm going to find K. I will constantly ask you to find rate constant K. So what we are going to do is we are just going to plug in some values from trial 1. Trial 1 always works. You could do 2 or 3, but we usually do trial 1. Let's plug in the concentrations for trial 1 and try to solve for rate law constant K. So our rate in trial 1 is 0.04. K is what we're solving for. Concentration of A was 0.1. Don't forget to square it. And concentration of B was 0.1. And we just got to take it to the 1. No big deal. Okay? So what we're going to do is we're going to go ahead and we are going to get K by itself. 0.1 squared times 0.1 on both sides. 0.1 squared times 0.1 on both sides. And K should equal 40. So that is our rate law constant. But another challenge of figuring out rate law constant is figuring out the units. Okay? The units, you could go ahead and you could just do molarity over second for rate, and then you could do molarity squared times molarity is molarity to the third. If you take molarity over seconds divided by molarity to the third, you'll get seconds to the -1 times molarity to the -2. Or we could just do a little shortcut and figure this out on our own. Okay? So, if a reaction is 0 order, K will have no units. Right? If the reaction is 0 order, it will have no units. If the reaction is first order, the units will be S to the -1. Okay? S to the -1. If the reaction is second order, the units of K will be S to the -1, molarity to the -1. And then if the reaction is third order, it'll be S to the -1, M to the -2. So you could start to see a pattern here. If 0 order, there's no units, that's pretty easy to remember. But after that, it's always going to have a s to the minus 1, right? First order has a s to the minus 1, second order has a s to the minus 1, and third order has a s to the minus 1. And then if it's second order, we add a molarity to the minus 1, and if it's third order, we add a second molarity to the minus 1, giving us a molarity to the minus 2. Okay? And then as you can see, if you were to add up these exponents here, they correspond to what order you're in. They're just the negative version of that. So since our reaction was third order, we are going to make it s to the minus 1, m to the minus 2. And that is determining rate law. Okay? Sometimes they want you to put k in for the rate law. Usually I just see your rate law written as this, and then they'll ask you to solve k later, where you will put in 40 s to the minus 1, m to the minus 2. So let's do a couple more examples of this. Alright everybody, so here's our next example. So what we see here is we see a table with some concentrations, some where they change and some where they vary. So I'm going to be thinking that I'm going to have to figure out how to find this rate law using the differential rate law process. Okay? So it wants us to find rate law, overall order of the reaction, and k with the proper units. Now notice in this example that we are no longer dealing with just the obscure chemicals of A and B. We are dealing with nitrogen monoxide and hydrogen gas. So when we write the baseline for our rate law, we are no longer doing rate equals k times A times B. It's going to be rate times NO to the N and H2 to the M. Okay, make sure that if they give you an actual compound, that you are using that actual compound in your rate law. So let's go ahead and let's start solving for this, right? We're going to try to find two trials where the concentration did not change at all. So right away I can see that in trial 2 and 3, the concentration of NO did not change. It stayed 0.6 for that trial 2 and 3. So that means that NO did not change the rate at all during those trials. But luckily, we could cover those up now and focus on H2, which did change concentration during those two trials. So if we're looking at H2 here, we see that it went from 0.35 to 0.70. So this concentration doubled. And since we're dealing with H2, I'm trying to find exponent M. And then during that time, it went from 2.835 times 10 to the negative third to 5.67 times 10 to the negative third. So you could plug that into your calculator if you want. You could divide 5.67 by 2.835 if you wanted. But I can tell that it just effectively doubled as well. So when we double the concentration of H2, the rate doubles. So this is a first order reaction with respect to H2. Okay? Now we got to figure out NO. So let's go to H2 and see where two trials were kept the same so it didn't affect the rate. Well, as you can see, in trial 1 and 2, H2 was kept the same, but NO was not, so we could say here that we can see how NO changed the rate. Okay? So we're looking here and we see that NO goes from 0.3 to 0.6. So NO doubled as well during those trials. But then we go ahead and we look at the rate. Did the rate change at all? I'm looking at this guy and they look the exact same, so the rate did not change. So it just was 1, right? The rate didn't change at all, so we're just going to say that as 1. Well, if I change the concentration and it does not change the rate whatsoever, to make this a true equation, we would have to change N to 0, right? Seems that NO does not affect the rate of this reaction whatsoever. It's just hydrogen gas. We doubled the concentration, didn't affect the rate at all. So it is 0 order with respect to NO. So if we are going to write our rate law here, we are just going to make it rate equals K H2 to the 1, right? NO to the 0 is just 1, so it doesn't affect the rate whatsoever. So that is our rate law. Overall order, we add up all our exponents. Our overall order is just 1, So it's just first order overall. And now it wants us to find K, so all we're going to do is just plug in some numbers from trial 1. NO doesn't matter, right? We figured out that doesn't change the rate at all. We got 0.35 for H2, and we got a rate of 2.835 times 10 to the negative third equals K times 0.35 to the 1. Right. And here it's pretty simple algebra, right? 0.35 to the 1 is just 0.35. So we'll divide by 0.35 by both sides. I'll plug this into my calculator because I cannot do this in my head. Divided by 0.35, and we should get a K value of 8.1 times 10 to the negative third. Right? 1, 2, 3. Yep. What are our units going to be? Remember, if it's zero order, there's no units. If it's first order, it's s to the minus 1. We went second order, it'd be s to the minus 1, m to the minus 1. If it was third order, it'd be s to the minus 1, m to the minus 2. Okay. And then if you wanted to, you could go ahead and plug that k into your rate law so that you would have a total equation to get rate for any reaction. So I would stick with this for your rate law. First order overall, and your K is 8.1 times 10 to the negative third seconds to the negative 1, or 1 over seconds. Okay? Let's do one more example. Let's make it a little bit tougher. If you want to pause this here and find rate law, overall reaction, and K with proper units, go ahead and give it a shot. But I'm going to go ahead and go through it right now. Remember, we are trying to find rate law, overall order, and C is just find K with proper units, of course. Alright, so here we no longer just have 2 reactants, we have 3 reactants here, okay? So our rate law is going to have a foundation of no longer just 2 reactants in there, but 3. So we got a bromate ion. We'll say that could be to the N. We have a Br ion, which we'll say will be to an M. And we have an H plus ion, LMNO. Let's make it P, okay? To the P. So that's what our rate law will look like just with solved NM and P. And hopefully a K later on as well. So we are looking at this, and what we are going to do, remember, we got to keep 2 of those concentrations constant while we change the other concentration. That way, we know that those other reactants aren't affecting our rate whatsoever. So if I go ahead and I look at trial 1 and 2 right off the bat, I see that we didn't change the rate for Br minus or H plus at all during those reactions. So I know that this is a good time where I can see that the bromate ion is the only thing affecting the rate. So I am not caring about Br minus and H plus. I am right now focusing on BRO minus. So I'm looking at BRO minus, and I see that the concentration has doubled. Okay? So for BRO minus, I'm going to put a 2 to the N. And I notice that as the concentration doubled, the rate also doubled. 8 times 10 to the negative fourth times 2 is 1.6 times 10 to the negative third. So that must mean that with respect to bromate, this is first order. Okay. Let's go ahead and look at Br minus. Let's try to find 2 trials for Br minus where BrO3 minus didn't change and H plus didn't change. Well, I'm looking here, and I see that in trial 2 and 3, bromate didn't change and H plus didn't change, but Br minus did. So I know that in trial 2 and 3, bromate and hydrogen didn't affect the rate, only bromine did. So once again, we're going to take a look. We're going to see that bromine doubled, so I'm going to put a 2 down here with a M on top. So bromine doubled, and if we look at the rate, it went from 1.6 times 10 to the negative third to 3.2 times 10 to the negative third. That looks like a double to me. So M must also be 1. It must be first order with respect to Br minus. Now, let's focus on H+. H+, oh, look at that. It looks like that it stays the same pretty much except for trial 3 and 4. It looks like bromate. Uh-oh, we can't use that one either because these guys haven't stayed the same. Let's see here. Where's one where bromate and bromine stayed the same, but hydrogen did not? I'm looking at this. I see that trial 1 and 4, bromate stayed the same. And in trial 1 and 4, bromine stayed the same. So I will cancel out those guys, and I look at hydrogen, and it looks like it did change. So we know that these guys were not a factor in the rate, but hydrogen was. So if we're looking at hydrogen, it looks like it doubled. I'll put a P to the top there. And in trial 1 and 4, while the concentration doubled, the rate looks like it quadrupled. Okay, it increased by a factor of 4. So that means with respect to H, it is second order. Okay, you will never see a reaction that's fourth order. This is theoretical. Okay, it's just too much going on to affect the rate. There's a lot more factors going on with real reactions. So this is purely theoretical, but still works. Okay, so here is our rate law without the K. First order to bromate, first order to bromine, second order to hydrogen. A lot of numbers, you just got to break it down. Overall order, we got 1, 2, 3, 4, so it is fourth order overall. Again, not an actual order you will see in real life, not an order they will hit you with on the AP exam. And then we got to find K, right? We got to find K. So let's go ahead and just plug in what we know for the rate law down here. Let's use trial 1. How about it? We got a rate of 8 times 10 to the negative 4. We got a bromate concentration of 0.1. We got a bromine concentration of 0.1. And we got a hydrogen concentration of 0.1. So, pretty much it's like 0.1 times 0.1 times 0.1 times 0.1. So we're going to go ahead and divide by all these guys. 0.1, 0.1, 0.1 squared, which is just 0.01, but I'll leave it as is. And we should get K. Let's go ahead and let's figure this out. I think I have an idea of what it is, but I just want to be sure. 8. Okay, so our K is equal to 8. Now, we got to figure out those units, okay? We got to figure out those units. Remember, if it's zero order, it is no units. If it's first order, it's s to the minus 1. If it's second order, it's m to the minus 1. If it's third order, it's m to the minus 2. So in this case, if it's fourth order, it must be s to the minus 1, m to the minus 3. Okay? So we have found overall order. We have found K. And for rate law, I am just going to put rate equals 8, s to the minus 1, m to the minus 3. Bromate, that is first order. Bromine, that is first order. And hydrogen, which we figure to be second order. Okay? So that is differential rate law. We are using experimental processes to figure that out. we are keeping some concentrations the same while doubling others to see how it affects our rate, and effectively coming up with a nice rate law that helps us explain the overall rate of a reaction, no matter what kind of concentration we have. So now we could put 0.30 concentration, and then 0.60 concentration, and 0.02 in hydrogen, and we can effectively be able to tell how fast that reaction will happen. So that is differential rate law. There's some practice attached to give it's a go on your own to see how you're doing. And that's it, guys. Have yourselves a great day.